So we'll go through the problems that were at the end of the last lecture. So this will be solutions 1. Alright, we had a 12 volt power supply with a 1k resistor or 1 kilo ohm resistor, 1000 ohms, and we needed to find the current and the power. So using V equals IR, what we can do is divide voltage by resistance to find the current. So what we have is 12 volts divided by 1000 ohms. And that gives us 0.012 amps or 12 milliamps. Then what we had to do was find the power. Now we can do that using P equals IV, now that we know the current and the voltage. So we've got 0.012 times by 12 to give us our power output, and we'll just jump to a calculator, and I'm using Octave again, and I can just type that in here, and this gives us 0.144 watts. So here what we've done using V equals IR, we've found the current and we've found the power output. Looking at the next question, we had a resistor with 0.002 amps going through it, and it's a 30 ohm resistor. We needed to find the voltage and the power. So what we can do is, again, using, want that in black, V equals IR. Well, we know the current. The current was 0.002, so 2 milliamp, and a 30 ohm resistor. So (0.002 times 30) gives us 0.06, so 60 millivolts. Then we had to find the power. We can do that using P equals IV. We've got a current of 0.002 and a voltage of 0.00 or 0.06, so we can multiply them together. Put them in the calculator. And we get 0.00012. Yeah, 0.00012 watts. So that's 120 microwatts. So here what we've done, we found our voltage, we found our power for this circuit. Looking at the next one, we've got component A, requires 3 watts and has 200 ohms internal resistance. We need to find what voltages across this to make this run, and what current goes through this to make this run. So we've got 3 watts, an internal resistance of 200 ohms. So what we're going to do is create a P equals IV and V equals IR, and then rearrange them. So we've got a power equals 3, and we had a resistance of 200. We've got P equals IV, V equals IR. So I'll rearrange this. We know the resistance, we know the power, we want to find voltage and current. So I'm going to rearrange this one here to find current. So we've got V over R equals I. We'll substitute this in for this I here. So we've got P equals V squared over R, because V times V gives us V squared. Now what we can do is rearrange this. So we've got P times R multiplying both sides by R equals V squared. So the voltage is going to equal the square root of P times R. We know what P is, we know what R is. P times R is 600. Root 600 will give us our voltage. Put that in the calculator. So we've got square root of 3 times 200. And that gives us 24.49, so roughly 24.5 volts. Root 3 times 200, and that was 24.495 volts. So now we know the voltage, we can substitute it into either of these equations to find the current. So we've got power divided by the voltage gives us current. P over V equals I. So that's 3 divided by 24.495 is our current. Put that in the calculator. So we've got 3 divided by our previous answer, 24.495. That gives us 0.122 amps. Now, just to validate that, we can put it in this equation here. In this case, we do our voltage divided by our resistance. So if we did V over R, we should get the same answer, and we'll just validate that quickly. So we've got our 24.495 divided by 200. 24.495 divided by 200. And as we can see, it gives us roughly the same answer. There'll be some rounding error in there. So that also gives us our 0.122 amps. Just quickly, that rounding error will come from the software itself holds this data to much higher decimal places than it actually displays on the screen. So there'll be more decimal places in this answer that it just doesn't show us. So when we come to this stage, this is the one calculated with the answer with many decimal places that we don't see. And this is me rounding it to what we see on the screen, which is the cause for the different answer. So what we've done for this component, we've calculated the voltage and we've calculated the current twice and validated our answer. And it's always worth doing that just to make sure you haven't made a mistake somewhere in the calculations. Let's have a look at the next one. We've got a 1/4 watt resistor. Are we within the design spec? So what we have to do is find the power dissipated by this resistor and see if it's under 1/4 watt. So this here is going to be 0.25 watts. And we can do our V equals IR, P equals IV. What I'm going to do is do that same rearrangement. So I've got P equals IV, V equals IR. And again, we'll eliminate I from this equation on the top here. So we've got V over R equals I, dividing both sides of this equation here by resistance. And then we can sub that I into this top equation here to give us P equals V squared over R. Now we've got P equals V squared over R, we can just put in our values. We've got a resistance of 330, a voltage of 9. And we'll just put this in the calculator. So 9 to the power of 2 divided by 330. And this gives us 0.245 watts. And that was 0.245 watts. So yes, it's within spec. Just. What's the max voltage we can put across the resistor? Looking at this equation here, we can rearrange it. Multiplying both sides by R gives us, we'll undo that, change colour back to black. Gives us P times R equals V squared. So V equals the square root of P times R. So in this case, this is going to be root 0.25 because we're looking at the maximum and the resistance was 330. So times 330. Put this in our calculator. So we've got the square root of 0.25 times 330. So we get 9.083 volts. So just a little bit over 9 equals 9.083 volts. So what we've done is we've confirmed that it's just about within design spec, and we could increase this by about 83 millivolts to take it to the maximum rated power. Let's look at this question. A heater operates at 1 kilowatt from a 12 volt battery. What's its internal resistance? How much current is flowing through it? So let's just sketch this one out. So I'm still in red. We've got a 12 volt battery. 12 volt battery going through some kind of heater. Which dissipates 1 kilowatts. So that's 1,000 watts. And we're down at the ground here, so 0 volts. What do we want to find? We want to find its internal resistance. So we can go in, we know P equals IV, V equals IR. Same rearrangement again. V over R gives us our I, and we can sub it back in. So V over R equals I. We can sub this one back in. So we end up with P equals V squared over R. We want to find the resistance, so I can multiply both sides by R to give us PR equals V squared. And because I'm looking for the resistance, I can divide both sides by power. So my resistance is going to equal V squared over P. Once we know that, we can put this in the calculator. So we've got 12 squared divided by 1,000, and that'll give us our resistance. 12 squared divided by 1,000, and that gives us 0.144 ohm. All right then, what else does it want us to find? It wants to find how much current is flowing through it. So we can use V equals IR up here to find our current because we know our resistance and we know our voltage. We can do the voltage divided by the resistance to find our current. So we've got V over R equals our current. We can put that in a calculator. We've got 12 over 0.144. 12 divided by our previous answer, which was the resistance. And that gives us 83.33 amps. So what we've done is we've rearranged to find our resistance, and then we've put that into V equals IR to find our current. Let's look at the next question. Assuming the previous battery discharges at 12 volt until empty, so we've got a curve that looks a little like this, where this is voltage. Oh, I'll switch back to black. Where this is voltage, this is time, and it'll discharge constantly at 12 volts until it runs out of power. So we've got a curve like this. As I said when I was explaining the question, typically batteries don't have curves like this. They have more complicated curves where they dissipate gently over time. So a typical battery curve. And this is voltage against time, would look something like this. Whoop. Where this would be the kind of rated voltage, and there's time on the bottom. So we're just using this for our question, our example. Now, it has 500,000 coulombs of charge. How long will the heater run? So and our charge, which is Q, equals 0.5 times 10 to the 6, and that's just saying it's 500,000. 10 to the 6 is a million. 0.5 times 10 to the 6 is 500,000. So we know an amp is a coulomb per second. We are looking for seconds, so we can multiply both sides by seconds. So an amp second is a coulomb, and then we can divide by current. So we get our time, our seconds, is going to... this should be T. We can divide both sides by current to give us T equals our charge divided by our current. Putting the numbers in, we've got, and using this equation, if we take 0.5, so our time is going to equal 0.5 times 10 to the 6 divided by our current, which if we check back to the previous question was 83.33 amps. And it was 333 amps. We'll just add that in, extra decimal place. And now we can put that in the calculator. So I come in here. Helps if I remember the numbers. 0.5 times 10 to the 6 divided by 83. So we've got 0.5 times 10 to the power 6. And we'll divide all of this by our previous answer, which was the current. And this gives us 6,000 seconds. 6,000 seconds divided by 60, because there's 60 seconds in a minute, gives us about 100 minutes. And we'll leave the answer in minutes. You can divide that again by 60 to work out how many hours, but 100 minutes is a nice number. So our time is going to equal 6,000 seconds, and that gives us, was 10 minutes, 100 minutes. "100 minutes is the total runtime of the battery." So here's our answer. So by knowing the charge on the battery, we can work out how long it'll drive this heater. Okay, so that's the answers to all the questions. Thank you very much.